We are going to my last class today. I'm going to speak about multidimensional social models. In particular, I will focus in two models, a classical one, which is the axonal model, which is discrete, and a new one, so discrete and a classical one, another one. And a new one that is not discrete is with continuous variables. And this very new one is from last year publication. So we are going to see two different way of thinking these kind of problems. Okay. I don't know. Every time I just go to another level of problems. Okay. So the first model, the axonal model, which are going to see today, is about homogeneity and diversity in culture. And it addresses a problem in the way how culture is propagated and to understand how culture can get established, spread, and be sustained as a growing importance in today's world. In particular, we are in favor of a common culture when it benefits for us, when it favors communication, prevents conflict, etc. But also, we hate to harm people, or we hate where some small culture disappear. So the problem of understanding how we can go from homogeneity to diversity in culture is a problem that was the motivation of this model. And the person who addressed this was a person that Marcelo cited yesterday, Robert Axelrod, is a professor of public policy, and he asked himself why if people tends to become more alike in belief, in attitudes and behavior, which is the dominant experience in those days, why do not all such different disappears we are going to a common culture. In order to do that, we have to define how can we frame culture in this kind of terms. The term culture will be used to indicate the set of individual attributes that are subject to social influence. The meaning of this attribute is not specified in the model, and the question that is going to investigate is how people influence each other on a given set of features and why this influence eventually does not lead to homogeneity. Okay? Sometimes it works, sometimes doesn't. So the idea surrounding the problem of axonal was that the transfer of ideas occurs mostly frequently between individuals who are similar in certain attributes such as belief, education, social status, and like. So the idea of the model, the axonal model, is to abstract this fundamental principle and so I get lost, sorry, to say that communication is most effective between similar people. I'm not. Why? The question is like that. Sorry. Why, if people get to interact more frequently with similar ones, and after interacting they become more similar, why we eventually can diversity of culture be sustained? Okay, this is the research question. And the idea of axonal is to propose a simple model to try to answer this question. Okay? This is what so he developed a theoretical model in which agent interacts according to this mechanism in order to solve this research question. Okay? This is the idea. So the axonal model is an agent-based model with local interactions that will produce global behavior. There are no central authority. There is adaptative rather using rational agents when, in the case of Marcelo, the individual are going to follow a very simple rules that are sketched here. The interaction between people is more frequent and intense if they are more similar. And this mechanism is called homophilia. The more similar they are, the more prone to interact they. And if after the interaction between people take place, they become more similar. This is a mechanism we call social influence. And the question is these two simple mechanisms can maintain social cultural diversity or just tends to an homogeneous global state. That's okay? This is the question of the model. And this was published in 1997, like a discrete multidimensional model, as I said before. And in the first version, it's set like that. We have a grid in which we place n agents. Each agent can interact with the local nearest neighbors, and each agent is defined by a vector of dimension f. And each variable in this vector can take q traits, q different traits. For instance, if we have 3 dimension and traits equal 2, we have all these 8 possible states. Each one of these units of the vector can symbolize, for instance, choices in language, politics, civil states, etc. And the higher is Q, the more options we have in every cultural aspect. Okay? And the interaction idea is the following. We pick up an active agent, we pick up and we elect a neighbor, and each one of them has a vector state, and they are going to interact with a probability which is proportionally to the similarity between them. Okay? If they have 2 features in common, they are going to interact with a 2/3 probability. And if interaction takes place, in the feature they are different, they become similar. So the blue agent will take the state of a red agent and then become similar. Okay? And this is the dynamics. In its other example, this agent will interact with probability 1/3, and they will change one of the 2 other features at random. Okay? And this is it. This is the dynamics. How? What is the question we ask? Which are the global states of this behavior and how it depends on the parameter? When we do that, we can see that if we fix the number of features, we have 2 kinds of behavior. One, for low values of Q, for instance, here is 5, if we perform a lot of interaction, the system will eventually converge to a monocultural state, as expected, because after each interaction, agents become more and more similar. But what is not obvious is that when we increase the number of traits, the system do not converge to a consensus, to a uniform cultural state, but the stationary state is a state of different cultures can coexist. And this is called a state of cultural diversity. Why they don't interact each other? It's a question for you. They don't share anything. They are orthogonal. That's okay. They don't share any cultural traits, so they can interact. They are orthogonal, okay? That's right. So the typical, we can characterize the way to characterize the global behavior of the system is through the size of the biggest homogeneous cluster. So if we plot the size of the biggest homogeneous clusters as a normalized, as here, or the size of the network, as a function of the number of traits, as a function of Q, we observe here a transition between a monocultural state to a pluricultural state. Okay? And in the transition region, there exists different size of different culture. Okay? And this is a critical group. So we can also perform this problem in a lattice from different values of number of features, and we observe that the transition not only depends on Q, but also depends on the number of features. Okay? What kind of transition is it? This is the question that a physicist can do, and the answer is that depends. It depends if the number of features is 2, this is a second order phase transition. If the number of features is greater than 2, at least in between 3 and 10, this is a first order phase transition. Okay? And this was investigated in 2000 and 2003, where, well, these very known guys, Matteo Marsili, Vespignani, and the group of Maxis and Miguel. How is the typical question of a statistical physicist? Do this transition depends on the underlying topology? They study this transition, the accelerometric transition, in a Watt-Strogatz model, in which they analyze the transition for different values of disorder, or of rewinding probabilities, and this is a kind of phase diagram with the solution in terms of the two variables, Q and P, and they found here a transition curve between these two states. Okay? Can we look at phase transition in scale-free networks? Yes, this has been done, 2003. They analyzed how the transition depends on the size of the networks, and they also find scaling relations in which all could collapse for a given relation between Q and the size of the network. So, if there is a scaling relation in scale-free network, can we find a scaling relation in the two-dimensional grid? The answer is yes. And if there is a scaling relation, which are this scale relation and what told us about the problem? If we plot the size of the big cultural fragment as a function of this quantity, and this quantity is the probability of having interaction between neighbors at t equals 0, this is a measure of homophily, we find here a scaling relation for all these curves. So we can understand why depend on F and on Q, because this relation between F and Q gives the probability of having a link with 0 homophily at time equals 0. Okay? So this is a problem in which initial conditions are very important to the transition. So we ask this, if scaling of, if we can find the nature of this transition, and we analyze this kind of networks in the limit of infinite number of features, and we use the same scaling control parameter to analyze the transition, the phase transition in the fully connected networks. And what we found, and I will not detail here, that is a paper we did in our group 2 years ago, is that the acceleration transition in fully connected networks is equivalent to the transition of random networks. Some of you know the transition of random networks have a set of nodes, and I'm going to link 2 nodes with a probability P. If I increment the probability, the greater is the size of the connected component. And I have a kind of percolation transition there, where if we analyze the critical exponent of the transition, they are similar to those of the acceleron model in these limits, okay? The second question, can we obtain a master equation of the acceleron model? Of course, there are some work over there, but they have not been going through in fully connected networks. And I'm going to sit in here. Job of Lucia is here, and in which we analyze an analytical approach based on similarity vectors. And we also check that this kind of transitions is a very important initial condition to determine how is the transition here. There are a lot of literature in this model. Not so much as in the Butter model, but there is a lot. If you want, I can provide some papers. I just want to call your attention about the nature of the transition and how can we understand that it depends on a parameter f and a parameter q, how these parameters are related with some property of the model. And here, the relevant quantity, because they tell us if agent interacts or not, is the probability of interaction. So the relation of the probability of interaction at time equals 0 is a relevant quantity to analyze the transition of this model, okay? But of course, this was a toy model. It was used to many other applications. For instance, I could spend some 20 more transparency to show you papers where it can be used to analyze the influence of mass media in this kind of model. One of you did it. Where is? There? You, of course. You're very familiar with that. So this is a lot of literature using this kind of model to study how to incorporate the influence of mass media in social model. I'm not going there, but I'm going to go to another family of model. It's related to another class of multidimensional opinion model. There are more complexity to be considered besides the one that came from the acceleron model. And one of them is that topics are rarely discussed in isolation, okay? Individuals are more likely to have certain combination of opinions than others. For instance, if I am in favor to the construction of a wall separating Mexico and US, maybe I'm not in favor of having a transgender bathroom in every places. There are opinions that can be correlated and opinions that are not. And the correlation of opinion is what defines identities and ideological states. This is a measure, these are data taken from one page that this American National Election Studies in the United States, that they perform every year election. They do a lot of surveys, and there is a lot of data in which the question have different options. Typically, there are between 1 and 5 options, and one has to answer that. And this is this kind of data. So the question is, it is possible to model this kind of situation in which topics could be correlated? It's an important issue. Well, it can be modeled, but assuming that topics are not independent of each other. So we have to add some degree of complexity. In order to do that, we can do that, or the authors of the manuscript, the paper I'm going to show you, they do that with an orthogonal basis of topics, okay? And this idea, as the author said in the paper I will show in some minutes, is grounded in what happened when we have topic decomposition, when we analyze using natural language processing, when we analyze a large amount of news of text, a large corpus of data, as the one that Lucio shows in his presentation, and the natural decomposition of these topics are given by non-orthogonal directions in the semantic space. So it appears that non-orthogonality is a relevant question to understand how opinion in different topics appear, and these guys last year proposed a multidimensional model of opinion with non-orthogonal topics. So in the rest of the class, I'm going to show this, the main result of this paper, okay? Here is a paper of Bauman, Lord Spring, Sokolov, and Michel Starnini, one that published with Wesley over there. Agents are represented by opinion vectors. So each component of this vector is an opinion of a given topic. And these opinions are given by a continuous variable, as I explained in the second class, in the third class, sorry. Okay? Here, the opinions are not bounded because it is easier for the equations. And the sign of the opinion describes the qualitative stance of a leaning towards the topics that are discussed, and the modulus of each component quantifies the strength of his or her opinion about a given topic. That's okay? Are you following me? So the authors write down equation for any n-dimensional space. I will focus in two-dimensional space because it's easier. And here we have two different topics. For instance, right of same-sex couples and right of transgender people. And they are, for instance, correlated. And people can have opinions in different one of the topics. And the opinion in every topic of a given agent evolves like this. This is another way of formulating a model of opinion formation in which the dynamics is not given by simple rules, but it's given by a differential equation, okay? And this differential equation, what does it tell us? It tells us that every agent, if there were no coupling, if this term was zero, if k is zero, they decay to zero. Or it has to be, if there is not interaction, every agent goes to zero. Zero means neutral. Okay, that's right. Zero means neutral, plus positive is in favor of some topic, negative is against this given topic, okay? If we turn on the coupling, every agent is going to interact with the neighbors given by the adjacency matrix, as all of you know. And this interaction is given by this hyperbolic tangent in which they are influenced not only by the opinion of the other guys in the same topics that is termed here, but because the opinion of some guy in other topics, if these topics are correlated. Okay? This is the correlation matrix between the topics.
The correlation is the same for every individual? Or?
In this model, is the same for this individual. Yes. It's the same for this for all individual. Wait, I'm going to die today. So, relevant parameter of this. K, this parameter, this delta, that is the parameter that regulates the correlation between topics, and this parameter alpha. What this parameter alpha means? What these parameters regulate here? The weight of the correlation. The weight of the correlation is given by the parameter delta. This is a kind of, this regulates the weight of the hyperbolic tangent. If alpha is high, then small values of the neighbors will produce big influence in the agent Y. If alpha is low, this is going like this, and then small values of opinion of neighbors' agents will produce small values. The influence is a measure of how strong is the influence. They called the controversiality, because it could be topics that are more controversial, that small variations in one subject affects a lot of us, and there are others that not. So they called controversial, okay? So the question is how or which kind of global behavior this model produces.
Have the same alpha there.
Yes, they have the same as, yes. You can, yes, this is a simple model of this.
Okay.
And you are going to see that even though this model has a rich variety of behaviors. And that is the sequence that we all do that. When we start a framework, we start with a simple model, simplest positive model. And we analyze how is the behavior, and then we add complexity in several steps, okay? Of course, it would be more realistic if we put dependence to all of them, but the problem is going to be harder to analyze. Yeah. So first, I'm going to go to the simplest model. Just now how it behaves, and then go step by step, okay? When we look at the possible collective states of this model, we see that it has three collective states. It produces consensus when we have low values of alpha, and polarization. But we have two kinds of polarization. It could be uncorrelated polarization, with delta is 0 or has very low values, and every corner in this diagram is possible, or we have correlated polarization, in which have an opinion in one topic is correlated with an opinion in another topic, and the system go on to this corner or to this corner. Okay? And this is what authors call ideological state, because an ideological state is a set of correlated opinion about a set of topics. If we look at the dynamics, if alpha is going to is equal 0, they all go to the center, and if we increment the value of alpha, they can go from different corners with the same probability. The center is neutral. This is what is called neutral or consensus. Yeah, yeah, exactly. And if we turn we manage the correlation between topics, we can this kind of trajectories. uncorrelated correlation, and correlated correlations. But in this paper, the authors just don't rest in putting dynamics to the agents, but they also add dynamics to the networks. So in this manuscript, the network is also dynamics. Here, the contacts between individuals evolve in time according to a model that is called the activity-driven model. This is this paper over here. This model is very easy to understand. Each node has a certain activity, what is a parameter between epsilon and 1. Epsilon is the minimum degree of activity, and it is sorted with randomly with a power law distribution. And then, upon an activation, agent acts selected according to the activation level, and when an agent activates, they interact with m distinct agents with a probability driven by homophily, in the same way that the paper of Mas and Flachet, okay? And beta is the exponent of control this homophily. The higher the beta, the higher the homophility, okay? Okay. And this distance is the space opinion. First, they do a mean field approach in order to know how theoretically are the stable states. We can easily see here that x equal to 0 is a fixed point of the system of global consensus, and then the author performed a linear stability analysis in order to see which is the condition for this point is stable. This gives you a relation between the variables, in particular, if alpha is lower than this quantity, the system goes to consensus. Consensus is established fixed point. Otherwise, the system goes to polarization. Okay? If we numerically plot how the states are as a function of alpha and delta, we have this kind of diagram in which we have consensus, we have correlated polarization, and we have uncorrelated polarization. Okay? And the critical value of the border between consensus and no-consensus region is given by this cube. There is a pretty much matching between numerical and theoretical calculation, and this depends on this. If is a measure of the interaction, the parameter k, in the number of activates, the number of nodes that activates a connection times the average activity. This quantity is proportional to the mean degree of the network, and it depends here on delta, on the correlation between topics. If we plot how the asymptotic network looks like, they look like this. So we can have here coexistence of opinions, and we can have also the formation of echo chambers. Remember that in all the models we have seen in this course, echo chambers generally produce with a combination of network dynamics plus some mechanisms that reinforce distance between people. Okay? And it could be achieved with different mechanisms. The last interesting part is the author perform a qualitative comparison with data. They compare taking many of the questions of these surveys I told you before, the American National Election Institute, and they choose this by peers and they plot in this way here, and they just see that they have pair of questions with correlated polarization, pair of questions with uncorrelated polarization, and question with consensus, okay? So the idea is that this model can qualitatively reproduce different behavior observed in these surveys. So I'm going to finish here. I would like to thank all the members of the SOPHI group, Social Physics group. It was in the first going out in the 2021 in pandemia. Particularly, I would like to thank Fabio and Sebastián, who helped me with some material for the talks, and also are Lucio and Lucia that are over there. So thank you very much for your attention, and I hope to see your presentations this afternoon. Thank you. Let's perform an experiment. Thank you. No es suficiente. Thank you. We have a coffee break now. So. A ver si quién se paraba. Y se paró para ver quién se paraba.